Hi everyone, and welcome back. Before diving into how a neural network processes data, let's highlight one key aspect. Any input to a neural network, whether it's an image, audio, or text, must first be effectively translated into a form the network can properly understand. This numerical representation is essential for the network to make sense of that data. Picture a digit, scribbled onto a small square grid of 28 by 28 pixels. Because it's grayscale, each pixel has a brightness value ranging from 0, completely black, up to 1, completely white. This means our 28 by 28 image is basically 7084 numbers lined up in some order. It's not immediately obvious how that might help a computer see, but it's exactly the kind of input a neural network can work with. Think about it. If you look at a handwritten 7, you instantly recognize it. You can also recognize a sloppy 7 or one written at an odd angle. But a computer doesn't see the curved lines or corners the way we do. It only sees a matrix of values, each reflecting how light or dark a specific spot is on the grid. Now, this principle doesn't just apply to images. Consider audio. When you speak into a microphone, the sound wave you produce can be captured as a fluctuating signal over time. If you zoom into that signal and slice it up into very small time intervals, each interval has a measurable amplitude. In other words, you get a list of numeric values representing how loud or soft the sound is at each slice of time. If someone is saying hello, the computer doesn't see a friendly greeting. It sees a sequence of amplitude numbers that reflect the contours of that spoken word. From those numbers, the network can eventually learn patterns, like which sounds map to which words or phonemes. Finally, there's text. When people hear about large language models, they often imagine that these models deal directly with words or phrases. In reality, text is broken down into pieces called tokens. A token could be a single word, part of a word, or even just one character, depending on the model's design. Each token is then represented as a list of numbers, capturing its identity and characteristics that contribute to the model's understanding of context. These numeric sequences allow the network to process whole sentences and paragraphs. So, whenever you want to teach a computer to do something human like, you first have to convert the raw data into numbers. It might be brightness levels of an image, amplitude slices of a sound wave, or tokens from a string of text. Once those numbers are in place, the neural network can apply its mathematical machinery to learn whatever patterns are relevant to the task at hand. In this video, we'll zoom in on a single neuron and explain why, despite simplicity, it's the key building block for the entire network. So, if we pick out one neuron, what is it really? The most straightforward way to think about it is that a neuron is a small machine that takes in some input numbers and then it spits out a single number between 0 and 1. These input numbers are usually the outputs from neurons in the previous layer. But even though it might sound trivial, there's a surprising amount of ingenuity in how this transformation happens. Let us imagine a bunch of inputs flowing in from the left. Each input is just some number. The neuron weighs these inputs differently. Some inputs might be multiplied by larger weights, meaning they're more influential. Others get smaller weights. Then, the neuron sums everything up into a single value. We sometimes call this a weighted sum. That sum could be any value: positive, negative, big or small. Yet our neuron wants to output something between 0 and 1. So after adding things up, we apply a squishing function, such as the sigmoid. If the sum is large and positive, the output is close to 1. If the sum is largely negative, the output gets pushed near 0. And if the sum is around 0, the output lands somewhere in the middle. We might also add something called a bias, although it is not shown in this video. Bias is a small number that shifts the sum up or down before we apply the squishing function, just to give the neuron a little extra flexibility in how it lights up or stays dim. That's really the gist of it. Multiply inputs by weights, add them together with a bias, and then push everything through a function that crunches it down into a range from 0 to 1. We call this final result the neuron's activation. It's literally just the number that the neuron fires off as its output. This is all an artificial neuron is, a simple function that spits out a number. The interesting part is that when you connect many of these neurons together, you get what amounts to a much bigger machine, an entire neural network. Each neuron feeds its activation forward to neurons in the next layer. Those neurons then produce their own activations, and so on, until you reach an output. Hence, you can think of a neural network itself as one giant function that transforms an input, like a list of pixel brightness values, into an output, like a digit label. Even though this single neuron setup may seem too basic to do anything interesting, chaining billions or even trillions of them together in layers is precisely what allows the network to learn complex patterns. The beauty is that each neuron's weights and biases can be adjusted until the entire network can map its inputs to the right outputs. That is the learning part of machine learning. But for now, all you really need to know is that a neuron is just a function. It inhales numbers, mixes them up with some learnable parameters, and exhales a single number between 0 and 1. In the next videos, we will talk about how neurons line up in layers, how information flows through them, and eventually, how they learn the right combination of weights to do things like recognize handwritten digits. So far, we've seen how a single neuron works. It takes in numbers, multiplies them by weights, and adds up those results with a bias. Then, it squishes the sum into a value between 0 and 1. But how do we go from individual neurons to a full-blown neural network? One that can recognize handwritten digits, or, more generally, solve whatever problem we throw at it. To picture it, imagine the example from our previous video, 7084 pixel brightness values for a 28 by 28 image. They form the first row of our network, or the input layer. Each of these inputs go into multiple neurons in the next layer, and each connection has its own weight. Every neuron in the next layer outputs a number between 0 and 1, just like we discussed. Then, those outputs fit into yet another layer, and so on, until you reach the output layer. In our digit classification example, the final output layer might have 10 neurons, one for each possible digit 0 through 9. They are also represented by values from 0 to 1. Whichever of these output neurons has the highest output value is effectively the network's guess for what digit it's seeing. What's the goal of this whole architecture? Simply put, we want a function that maps inputs, like pixel values, to outputs, like the correct digit. A neural network is our way of designing such a function. Each weight is a little dial we can turn to adjust how strongly one neuron's output influences another. The more layers and neurons we have, the bigger the network is, and the more dials, or weights, we have to tweak. This leads us to a crucial point. The entire network, from input to output, can be described by the collection of all these weights and biases. When you hear people talk about a model with, say, 8 billion parameters, they're talking about 8 billion individual numbers, these weights and biases, inside the network. Each parameter can be updated during training so that the network better performs the task at hand. That enormous table of numbers is the model. When we say an AI model, we mean that it's that massive set of numerical parameters plus the layout of how they connect through the neurons. It might seem incredible that adjusting so many individual numbers by just a little bit here and there can lead to something that recognizes digits, understands speech, or writes coherent text. But the principle remains the same. Each neuron is a small function, and together they form one big function. Modern neural architectures use a few clever tricks, and we will talk about them later. But whether it's 100 parameters or 100 billion parameters, the underlying idea of adjusting weights does not change. Neural networks are sometimes described as universal function approximators. They can, in principle, represent a wide variety of functions, so long as we pick the right architecture with enough neurons and layers. Of course, the big question is, how do we find the right setting of weights to make the network do what we want? Also, Why does this arrangement of neurons learn so effectively from examples? We'll learn about that in the next videos. Now the question is, how do we exactly tune all those weights? After all, the entire purpose of the network is to get from an input, like the 7084 grayscale values, to a correct output, like which digit the network thinks it is. In practice, you show it many examples and let it learn which arrangements of weights work best. That learning process is driven by two essential pieces of machinery: cost, or error, and backpropagation. Imagine you show the network a digit, let's say a 6, and watch as it produces some guess. Maybe its final layer output numbers look like 0.2 for 0, 0.1 for 1, or 0.9 for 4, and so on across all 10 digits. Ideally, if the input was a perfect 6, we'd want the network's neuron for 6 to light up close to 1. But our 6 neuron only lights up with 0.1, and it's not good. We need some way to quantify just how off the network's guess is. That's what the error or cost function does. One common way is to look at each output neuron and compare it to what we wanted it to be. If the correct digit is 6, the target output for that neuron is 1, and for all other neurons, the target is 0. The difference between each neuron's actual output and its target gets squared and summed over all neurons. We call that total sum the cost for this single example. The bigger the cost, the worse the network's guess. If the network is spot on, the cost is tiny. Now we have the target: minimize the cost. But how do we find which of the many weights and biases need adjusting, and by how much? That's the role of backpropagation. The key idea is that each weight in the network influences the cost, but not all weights are equally important. For a specific input, some weights have a large effect on the final output, while others barely move the needle. Backpropagation calculates exactly how much each weight contributes to the overall cost. It's like asking, who's responsible for this mistake, and assigning blame accordingly. We start with the output layer and work our way backward through the network. For each neuron in the output layer, we compare its actual activation, like 0.1 for the 6th neuron, to its target value, which should be 1 for the digit 6. If the neuron is underactive, backpropagation determines how much to increase the weights of the connections feeding into it. If it's overactive, it determines how much to decrease them. This process propagates backwards layer by layer, updating the weights of every connection along the way. And we don't stop at one example. In digit classification, we often have thousands or even tens of thousands of labeled examples. We feed each one in, compute the cost, and then average those costs to get a sense of how wrong the network is overall. The goal, of course, is to tweak the weights and biases so that this average cost is as small as possible, meaning the network gets most digits right most of the time. Eventually, the weights settle into some configuration that gives low error on the training set of examples. If all goes well, it will do well on new images it's never seen, showing the network has generalized what digits look like rather than just memorizing. Let's step back and look what happens when our neural network faces something completely outside its training experience. In previous videos, we focused on feeding the network clear pictures of handwritten digits, photos or scans of people's real zeros, ones, twos, and so on. The network learns patterns from these images, adjusting its weights for backpropagation until it can recognize digits with impressive accuracy. During training, our digit classifier only ever saw digits, and it was always required to pick 1 out of 10 classes, 0 through 9. So if you feed it something bizarre and meaningless, it will still choose a digit. Worse yet, it might be absolutely certain it sees a 5 or a 7. In reality, though, that random noise looks like nothing at all to us. That might sound surprising, but it actually illustrates a more general phenomenon. A model's behavior is always a reflection of the data it was trained on. Sometimes that leads to an answer that sounds right, but isn't. Our true aim in machine learning is not just to recognize the training examples perfectly, but to handle new, unseen data, a property called generalization. For instance, if you train a digit classifier on thousands of handwritten ones, it should still recognize a fresh one it's never seen before. The same principle applies to more complex tasks like speech recognition or language modeling. To achieve this, you have to show the network a balanced variety of examples. If you only train on neat, identical ones, the network might panic when it encounters a sloppy or stylized one. This is called overfitting. Conversely, if you fit it totally unrelated images, or don't repeat the training examples enough times, it might struggle to latch onto any defining patterns. This is underfitting. You want examples that are similar enough to represent meaningful variations, yet not so varied that the network has no coherent structure to learn from. And you must repeat these examples over multiple passes, or so called epochs, so the model truly absorbs and generalizes the pattern it sees.